The people we're going to hear from tonight are people who are really leading their fields in an area that involves trying to understand how human minds work, and often that connect our understanding of how human minds work to what we understand about artificially intelligent systems and how we can get them to work. And in particular, in domains where the intersections of those ideas are really having fundamental impacts in society. Some of those impacts are super exciting and just cool, and I think people should hear about them. I mean, to me, it's astonishing that I can talk to my speaker in my kitchen and get it to play the Beatles to me, or that I can tell my phone where I need to go and it will figure out what the traffic patterns are and give me the shortest routes and predict within about a 10-second window how long it'll take me to get there. These are just amazing innovations that have been brought to us by the intersection of cognitive science and artificial intelligence. And at the same time, I think there's probably validly a lot of general concern and misunderstanding about ways that this kind of science might be being abused in our society, ways in which what we understand about how minds work and how we can design algorithms might be being used to sway elections or to cause people to believe things that aren't true. Further, there's a huge amount of potential that we're all aware of if you have kids or grandchildren in school, where this kind of science offers the potential to make educational advances very widely available to people who otherwise couldn't afford it, or to help your kid who might be struggling in particular ways, learning to read or learning how to do math, but actually understanding what works and what doesn't work, and what systems you should invest your money in and what systems are kind of snake oil is really hard for people to figure out. So I think there's generally, as the crowd in the room attests, there's a lot of public interest in these kinds of issues. And from my point of view, as a scientist here at UW-Madison who studies these things, there's a paucity of information in the kind of popular press that's really accurate and at the cutting edge of what's really happening in this world. Today, we're here because many of you may not know, but Madison was just host to the International Meeting of the Cognitive Science Society. This is an international society of scientists. It's the largest international conference that focuses specifically on understanding how minds work and studying that perspective from multiple different disciplines. And because of this meeting, we happen to have some real stellar scientists in this discipline in Madison. And as one of the organizers of that meeting, I wanted to take the opportunity to say, these people are in town. Let's just have them come and talk a little bit about the kind of work that they're doing, the way that it intersects with things that are happening to all of us in our society right now, and to give you guys the chance, which what I view as really a kind of once-in-a-lifetime opportunity in a way, to speak directly with and ask questions of some of the scientists who really know about what's going on in these different domains. So that's what we're here for tonight. I've asked our speakers just to prepare some comments on their, some high-level comments on the kind of work they do and why it matters. After each talk, we're going to have the opportunity for some questions, and the hope is that at the end we can have some sort of integrative discussion about these kinds of issues with the audience and amongst the panelists themselves. So let me just briefly say who we're going to be hearing from. We're first going to hear from Matt Botvinick, who's here from DeepMind in London. DeepMind is an artificial intelligence company. Some of you may have heard in the news. It gets quite a lot of press because it's the company that, for instance, designed the first computer who could beat a human champion at the game of Go, which was a huge breakthrough in artificial intelligence, but is also responsible for many, many new and startling kinds of innovations in machine learning and artificial intelligence.
Hi everyone. It's really my pleasure to be here. As Tim mentioned, I work at this artificial intelligence company in London called DeepMind. I actually am a cognitive psychologist and cognitive neuroscientist by training, so I'm sort of a card-carrying cognitive scientist, and that's one reason I'm at this meeting. But I joined this company a couple of years ago because I was just very excited about what was happening in artificial intelligence, and also its implications for understanding the human mind and improving human life. And it's wonderful to be here to tell you about that, because I think one problem that we're having as a society right now is that we're trying to think through the implications of this technology that's developing so rapidly. But I think a lot of people outside of the AI community are getting their information about what AI is from Hollywood rather than from people who actually do AI research. So I'm going to take this opportunity to tell you about some things that are going on at our company that I'm excited about, and then I'll look forward to discussion about what the implications are and maybe how these developments fit together with other things that are going to be discussed. I should say at the outset that I'm going to talk about a bunch of stuff. Only a thin slice of it is really reflects my own contribution. DeepMind is getting to be a large company full of brilliant and productive researchers, and I'm just going to tell you about the stuff that all of them are doing, some of which occurred before I even arrived. I thought I would divide my time among 5 topics, just briefly touching on an example from each category. I'll start off by talking about an example of learning. We'll talk a little bit about planning, a little bit about imagination, a little bit about cooperation, and then a little bit about the brain. So let's start with learning. So DeepMind actually sort of first became well known due to some work that they published in 2015, actually before I arrived, in which they showed that they could build computer programs that could play classic Atari video games and play them better than human expert players. But the thing that was really cool about this was that these computer programs were not hand-built to play Atari games. Instead, these were learning systems that just that didn't know anything about Atari when they started out, and were just presented with an Atari game and were allowed to play and then improve themselves. So they got good at playing Atari by learning. And I just want to give you a glimpse of what's like beneath the hood, so this isn't mysterious anymore. So the way that we do most of our research at DeepMind, and this is becoming pretty widespread in the AI community, is by building what are called artificial neural networks. And these are inspired by biological neural networks. As many of you will of course know, biological neural networks are made up of neurons, which are cells that have these long tendrils and that end in little processes that emit chemicals called neurotransmitters. And so these are neurotransmitter releasing bits that are going to release chemicals onto this next neuron down the line, and those chemicals will either excite it or inhibit it. And that's how information transmits in the brain. Artificial neural networks just take that basic idea and formalize it and simplify it and allow us to build these kinds of things in a computer. So this is sort of a formal representation of that same thing. You have these signals coming in, which are supposed to represent the chemicals, the neurotransmitters, and then those signals are summed up. That's what this symbol means. They're added up. And then there's some threshold function that says, yep, there's enough. This adds up to a high enough number that I'm gonna activate. And then a signal is sent down this long tendril, which is like this long tendril, and sent to the next neurons down the line. And artificial neural networks just take this unit. This can be expressed with very simple math, and I'm going to like copy it into this. Let's just say, for the sake of brevity, that thing down there is the same as, it's just a re-representation of that thing up there, but I'm showing it in that way because now I can expand it and explain that when we build neural networks, we take this unit and we use it like Legos. We put together lots of these little units, both in parallel and in series, and this allows information to be transmitted and transformed to do interesting things. But the magic is that we have ways of training these systems to take inputs like images, as I'll explain in a minute, and we can train them to give outputs that we want. So we at the output end, we say, no, this is what we wanted at the output end. And then we have ways of changing the connections within the system, changing the synapses so that we get the outputs we want for any input. And this is actually a pretty old technique now, but it's come roaring back in artificial intelligence through some demonstrations fairly recently that can be applied to some really rich problems, including image classification. So that's a setting in which you actually literally tell the system what you want. You showed a picture of a cat and you say, I want you to say cat. You show a picture of a car, you say, I want you to say car. The way that we trained, or the way that my colleagues trained these systems to play Atari was totally different. Instead of telling the system exactly what to do, the only information the system got was the points, the rewards that are involved in Atari. When the system got a point, it was given a little reward, and it had to learn what to do based only on rewards. This is also an old idea. This is something called reinforcement learning, and people had been thinking about using neural networks along with this reward-based learning for a long time, but nobody had been able to get it to work. There was some classic work trying to apply this to backgammon that seemed very promising back in the 90s, but it didn't scale to larger problems. And the accomplishment at DeepMind was to get this to scale to larger, more interesting problems. And the way that that was done was by just taking one of these deep neural networks, deep meaning many, many layers, and feeding in an image, which is just what's on the screen in the Atari game, and on the output end, training it to output not a word, not a name of a picture, but instead a joystick movement or button press, and training this with reward rather than direct instruction. So this learning system could play the game and see what got it points and what didn't get it points, and then change its internal weights, its internal connections until it did better. The trick to get this to work, one of the tricks, actually came from neuroscience, and it's based on something called replay. Memory replay. So it's known that in the human and many animal brains, after an experience, either at rest or later in sleep, the brain will replay the experience. This is something you see in the hippocampus, for example. And so this is an illustration of this sort of thing happening in a I guess this is a rat or a mouse. I don't know my rodents well enough. I guess it's a mouse. So this is a mouse traversing this track, and these cells in its brain are firing as it goes along, and then when it gets to the end of the track, the whole memory replays. And it turns out that if you install that tendency in this kind of artificial neural network, it helps a lot with that reinforcement learning process. So that's an example of learning. What about planning? So an example that I'll use here is something that also came out of DeepMind and turned out to be even more to make a bigger splash. Tim already mentioned it, which is training a computer program to play the ancient board game of Go. Which, if you're not familiar with it, there's kind of a craze around this game in Asia, and it's much more complex than chess. And it was considered a problem that AI systems wouldn't solve for the next 20 years. And it was solved at DeepMind in the sense that a system learned to play it to expert level, again using these deep neural networks. So these kind of piles of layers are just meant to represent a neural network of the kind that I just described. And the people who worked on this project took an input that just represented where the pieces were on the board, fed it through this neural network, and then asked the neural network to say, well, what move would you make? And then trained another neural network in parallel to say, don't tell me what move you're going to make, just tell me how probable it is that you think you're going to win. And these networks were trained as the system played a bunch of games, many games, through reinforcement learning. So again, if the system won the game, then the weights in the system were changed in order to make it more probable that it would do the same thing again. And the deep neural network learned rich representations of the board position that allowed it to know what to do even in positions it had never encountered before. But unlike the Atari setup, that wasn't the whole picture. So this is just a re-representation of these neural networks that I just described on each step in the game, saying, well, here's what I think I should do, and here's how probable it is I'm going to win. But there was another half to the system which actually looked forward in time and actually anticipated. So if I'm in this position, let me think now. Well, if I do this, then I'll end up here. And if my opponent does that, then I'll end up there. And this develops into what's called a search tree, thinking about the future, planning. And the magic of the AlphaGo system, which is what this was called, was that the estimates of value, of how probable it is I'm going to win, were used to guide this search down promising avenues. And then the result of that search process, namely whether the game was won or lost, would feed back to train those neural networks. So there was this sort of like reciprocal training of these two parts of the system. And there was the whole setup was also reciprocal in the sense that the system learned by playing games against itself. So there was no need for anybody to train the system. The AlphaGo just played itself and got better and better as it went along. And interestingly, after a little bit of training, it acted like a novice Go player. After a little more training, it looked like an intermediate Go player. And then finally, after it had really matured, it started playing in ways that even expert Go players were having trouble understanding. So there was this interesting developmental trajectory. This turned out to be a big splash not only in the AI community, but also in the Go community and all over Asia. This is a press conference at the tournament where AlphaGo played against the world champion Lee Sedol. And if you're interested in the background here, I should mention that there's actually a documentary about this bit of AI work. And this wasn't produced by my company; it was produced by an independent group. But it's quite excellent. It's on Netflix, and it's just called AlphaGo. Okay, how much time do I have left? I haven't been tracking. 10 minutes? Good. Okay, good. Okay, I just want to make sure I wasn't running out of time. 10 minutes is perfect. Okay, so planning, by definition, is about thinking about the future, and so in a way, it's a form of, it calls on imagination. Now, in the game of Go, the imagination isn't particularly rich because it just involves thinking about adding pieces to the board. But there's other work out of DeepMind and other places doing related work that really, I think, engages the notion of imagination more richly. And I want to give you one example. So one form of imagination that psychologists have studied a lot is mental imagery. And a task that's actually been used in psychology is one where you show someone a picture of a scene, and then you ask them to imagine that scene from some other point of view. And people can do this just fine, as you would expect. And so one question is, can we get artificial neural networks to learn how to do this? Can they learn from experience how to translate their current observations into imaginative constructions, like what would I see if I viewed this scene from another direction? So if I gave the system this view of this underlying scene, and then I said, oh, but what would you see if you viewed it from this angle? The system should give me a picture that looks like that, and we can compare it against the ground truth. So DeepMind published a paper recently showing that you can do this, and here's a little animation explaining how it works. There's a neural network here that feeds into a set of artificial neurons, as will become clear in a second, and then those artificial neurons feed into a decoder network. And here's how it works. So you take a picture in a particular scene, and you give that picture to the encoder network. They call it the representation network. And that leads to a pattern of activity over a set of units, set of neurons in the middle of this network. Now maybe you give it a second picture, and you say, here's another view of that scene I want you to think about. And by the way, here's the angle that you're viewing it from. And then finally, you say, okay, now, given that side information, given that information I've given you so far, now I want you to imagine what that scene would look like from this particular viewpoint. You give it an indication of what the viewpoint is. I want you to think about like facing northwest. What would that scene look like? And you can train the system to give you the right answer by comparing what it puts out against the ground truth. So you can compare that, and then you can use these learning algorithms that we've been using in all these cases so far to change the weights in the system, to change the synapses until it starts to give you the right answer. And once you've done that, the system gets to be very good at imagining scenes from other angles. So you can, this is just showing you what the output would look like. But now if you change the query, if you change the question you're asking, you can get the scene from all sorts of different angles. So it really does seem like the system has develop the ability not just to represent a scene from one point of view, but to represent something about the scene structure, and then to use that to imagine what it would look like from every point of view. And this is actually pretty amazing because it really requires the system to understand a lot of stuff about lighting and shadows. And if you give it a picture that, if I give you this picture, you don't actually know what's behind this red thing. There could be another object behind there. And this system will imagine, if you give it another point of view where it has to guess what it would see in that occluded space, it will guess things. It will like put different objects there. So an example of how we can model imagination in maybe in a particular sense. Okay, another category, cooperation. So this is very recent work from DeepMind that models, that trains artificial agents to play the game of capture the flag. Many of you will know this game. You have to run to the opponent's base and pick up a flag, and then you're supposed to take the flag back to your base. But your flag has to be in your base in order for you to get credit for bringing the enemy's flag back. And so if your opponent has stolen your flag, the way to get your flag back is by tagging them. So this was turned into an artificial intelligence challenge, and we wanted to see whether these neural network-based agents learning from reward could learn behaviors that allowed them to do well at this game. And the punchline is that they did. They performed better than human opponents, even when you keep changing the map, you keep changing the maze that they're running through. The technology here is exactly the same as the technology I've been telling you about all along. The only difference actually is that instead of a neural network that just has units that flow into other units that flow into other units, now we have also backward connections and sideways connections. And this is important because it means that activity can flow in loops, which means that the system has memory. It can keep around information over time steps. And that's really important if you're in a situation where you have to remember where an opponent is, even though that opponent is behind you, or you have to remember where your teammate is, or you have to remember that the flag, the other team has your flag. We can unfold this, we can redraw this network like this to simplify it, input units, a bunch of intermediate units that all connect to one another in output units. And then we can take this and unfold it in time. And then that allows me to explain a little bit more about how this system works. It takes these pictures, the artificial agents get pictures of where they are in the scene. This is the little outdoor scene version of the game. And then there's a recurrent neural network. But what really made this work well was recurrent neural networks at different levels of temporal granularity. So recurrent neural networks that captured very fine-grained temporal events, and then other neural networks, recurrent neural networks, that were keeping track of longer timescales. That's something actually that we think is true of the brain as well. I'm going to skip this in the interest of time. And I'll just wrap up by telling you about one more line of work, another thing that's just been published recently. But it allows me to emphasize that there's a really interesting and kind of satisfying exchange going on between artificial intelligence on the one hand and psychology and neuroscience on the other. A lot of the technology I've told you about was originally inspired by neuroscience. I mean, it's not surprising we're calling these neural networks. Reinforcement learning, this learning from reward business, was also inspired by what we know about how animals learn from reward and punishment. And this continues, and now AI is also feeding back to inform neuroscience. And here's an example. So there are really interesting neurons in the part of your brain that helps you navigate the world that respond to where you are in space, but they do it in this really weird way that's referred to as a grid cell pattern. So what you're looking at here is red would indicate that the neuron is firing when you're at a particular location. So you can imagine that I'm moving like this, and there's a cell in my brain that's firing when I'm here, and then it stops firing, and then it starts firing again when I'm here. And if I painted the floor to indicate when it fires, I would get this really crazy hexagonal pattern. This is called a grid cell. And work at DeepMind recently showed that these grid cells emerge spontaneously in artificial neural networks if you just train the neural network to predict where it is from motion cues. So if I let you see where you are in this room, and then I asked you to close your eyes, and I led you around, and all you had was your vestibular sense of how you were moving, and your sense of from your legs where you've moved. And then I asked you to anticipate where you are, and then open your eyes and find out. That's the task that we gave to this neural network. And it turns out if you just train a neural network to do that task, you get these crazy grid cells, which provides an indirect explanation for why these crazy cells might be in your brain. The other piece of this work that kind of put the other half in place of the story is that if you build a larger neural network that uses these grid cell representations, and uses those to do reinforcement learning to learn to perform particular navigation tasks, those representations really help. Having those grid cells really helps the reward-based learning process solve the task. And I'm almost done, but I'll just show you an example of what can happen. So you can end up with an artificial neural network that learns to do something like this. So imagine an artificial agent that's in this maze, and of course it has a first-person view. It's down in the maze, and it's just we're getting a bird's eye view. And it has to find a reward. It has to find a goal. And it wanders around, and it finds its way through this doorway number 5, and wanders until it finds, oh, the goal is over here. Good, I know. And then you put it back at the start point, but now you open all these doors, 1, 2, 3, and 4. Instead of going back the way that it originally went, it'll say, oh, those doors are open now. I can just take these shortcuts and go directly to the goal, which is something that humans would naturally do, and we know that rodents even do it. But it's a really impressive thing for an artificial neural network to do because it indicates a really fundamental understanding of how space fits together. So that's a whirlwind tour of some of the things that I'm most excited about that are going on, at least in the research group that I participate in. I mentioned that none of the work that I have described, or not much of the work that I've described, was really due to me. There are too many people involved with it for me to give them all a shout out. But I just wanted to emphasize the team effort by showing you the papers and the many collaborators that are involved in this. That's it. Thank you. So we're going to do a couple questions now, or? Yeah, sure. Yes.
They're seeing what a human is.
Yes, exactly. And this is one of the things. So I mentioned that neural networks came roaring back in artificial intelligence a few years ago because it was shown that they could perform a very sophisticated image classification. They could perform well on an image classification problem. And that was partially because of the application of a particular kind of neural network, which is called a convolutional neural network. And the idea here, it's very much inspired by the way the human visual system works. The way that the human visual system works is there are feature detectors in your brain. In other words, there's a neuron in your brain that responds to, let's say, a particular combination of horizontal and vertical lines that might look like an eye. Okay, maybe there's another neuron that responds to something that looks like an ear. But the important thing is that when those feature detectors, there are many of them. So if I have an eye detector somewhere in my visual system, I have lots of eye detectors so that I can detect an eye if it's over there, or if it's over there, or if it's over there, and that way I can detect a face regardless of where it appears. And a convolutional neural network sort of insists on this sort of copying. If I'm going to learn this feature detector here, then I insist on learning it in all these different places. And that sort of seemingly minor innovation is what really helped solve this image classification problem. And it also helps, it also was important in the Atari work in allowing the reward-based learning system to process images, to take these complex pixel-based inputs and make sense of them. Yeah, that was part of the breakthrough. Yes.
There is a famous experiment like Jean Piaget asking children to showing a scene how it would look from another
Yes.
point of view. And children are able to do it on one shot. So my question was, in your experiment, did the machine see all the angles repeatedly? In which case, it's not a wonder that it's able to guess how it would like on another point of view.
Yes.
Or did it able to change, transfer to a new scene?
Yeah, that's an excellent question, and the answer is it's the latter, very importantly. So it trains on, it gets a lot of training data. So it sees many scenes, and it doesn't see every particular angle on any given scene, but it has a tremendous amount of prior experience with, here are two views, what should this third view look like? Okay, here's a new scene. Here are two views, what should this angle look like? But the important thing is, so it does get a lot of training, but the critically important thing is that once it's had this experience, you can give it a totally new scene that it's never dealt with before, in which unfamiliar objects are in unfamiliar positions, and it can deal with that. This is what we call training looking for generalization, and it's a critical part of the tests that we do. Yeah. Yes. Yeah, this is a major topic of conversation in AI research, and the mission statement for my company is we want to solve AGI, artificial general intelligence. So it's very much on everybody's mind that we're not done if we have narrow intelligence where we have things are certainly much more juicy than they were 5 years ago in the sense that
not only do we have, I mean, I didn't mention this, but the system that can play those Atari games can actually play all the Atari games. It's not just specialized for one. But if the system that's trained to play all of those Atari games has no idea how to play chess or even tic-tac-toe. And it's that kind of flexibility that we clearly would want from the learning systems that we're trying to build. And it's the same thing with the navigation agents, right? So it's impressive, at least I think it's impressive, that these capture the flag agents can play skillfully even when you keep changing the layout of the, so we've gotten beyond a certain kind of narrowness, but these agents are specialized for playing capture the flag. They don't know how to play tic-tac-toe either. And so one thing that my subgroup at DeepMind has been very focused on is something called meta-learning, or learning to learn, which I think is a very central part of what makes humans so flexible in adapting to new tasks. So it's not just that we learn how to play a single video game. It's not that we learn how to play 3 video games. What's important is that when I'm given a new, somebody says, hey, play this new video game, then I can take all of the stuff that I've learned in those previous experiences and leverage it to learn quickly in this new setting. And ideally, that kind of transfer to new tasks would be very flexible and would span the range of things that humans can do. So that's the goal, but you're absolutely right. We're not there yet. Yeah.
You started out by saying that you needed a reward for these things. If you don't provide a reward and the system itself seek a reward.
So you have to say what's rewarding. So this is a really important point in reinforcement learning research. When you set up the task as the engineer, you have to stipulate what is rewarding and what's not. So somebody, when they did the Atari game, had to say, it's rewarding when you get a point. They could have made a different decision. They could have said, it's rewarding when you don't get a point. But that, so there's a design decision there. Once you've made that design decision, then everything else follows automatically. You don't have to supervise the system and say, the way that you would supervise an animal that you're training to do tricks or something. You simply set up the task, you define when the rewards should happen, and then the learning system will explore. So this is a very important part of reinforcement learning, is exploring, trying things out, seeing what works. A vivid illustration of this is AlphaGo, which explored the whole game of Go simply by playing against itself. So someone had to say, it's rewarding when you win. And that was an important decision. But after that, everything can happen spontaneously.